Okay, hey, so it's week 6, and I've had a lot of really good conversations with many of you regarding your projects for the course. So thanks for keeping me up to date on that. And like I said, if you need a little bit of funding to build your physical project, we can definitely help with that too. So if you haven't started your project yet, let me know, because that's a big deal. It's a large part of your grade. It'd be nice to see. You don't necessarily have to build something, but you do have to show some calculations. So what I'm going to do now is run through just a simple payback analysis for a solar thermal technology. And this will be one of the problems in the book that we're going to write. This can be a whole page. It can be a whole lot better once this gets published and everyone understands the alternative ways of energy that we practice. Here it is. Okay. You are considering, because you're either a homeowner or a business owner or a contractor. You're going to consider installing a solar thermal technology to offset an existing electric heating system in your house. Okay, so here's what we got. Let's start with the house. Something to point out. And this is more common than you might think in Montana, but you might just have electricity. So you have kilowatt hours coming into the house, going through typically baseboard heaters. They're just big toasters, more or less. Some element in there that gets hot due to P equals I squared R. That's the Joule heating. It's bad if you want to have a conductor. It's good if you want to have heat in your house. But that's the equation for how much power comes off an electrical system as heat. Then, of course, the energy just equals the I squared R times the number of hours. And then the dollars equal the energy multiplied by the dollars per kilowatt hour. So that's kind of what we're up against. So let's first see what we're paying for this electrical heat. So let's go back to the problem. Your cost of electricity is 10 cents per kilowatt hour. It's a good ballpark for Northwestern Energy. The size of the heater is 2,000 watts. So we don't really know the details of the resistance and all that. We could back it out if we knew if it was a 220 or 110. But that's the size of the heater, and you're going to run it for an average of 4 hours a day. And let's see, so I'm going to assume that there are no thermal losses in either one of these. All the energy goes into into useful heat, and that you're not storing it. So the other thing I did not do, I just assumed that this thing is just kind of running 24/7. That's why I said calculate the number of days to simple payback. It could be that, hey, I only run it 1 day a year, and if your simple payback is 365 days, then you're looking at hundreds of years of payback. But if you're running this thing 4 hours a day, 365, your payback is going to be quicker. So first of all, let's just see what we're paying on a daily basis. So this is 2,000 watts. And we're running for, and the dollars per kilowatt hour are 10 cents. First, let's get the energy in here. So this is going to be dollars per day. So the energy per day equals 2,000 watts. Times 4 hours. And then the electricity bill, I just said it's a dime a kilowatt hour, so 0.10 per. Yeah, so there's your dollar symbol, 1.0, 10 cents per kilowatt hour. So let's just convert the watts to kilowatts. So 2 kilowatts times 4 hours times 0.10 dollars per kilowatt hour. So this is pretty nice, pretty simple. The kilowatt hours here, absorb that kilowatt hour there. 2 times 4 is 8. 8 times a dime is 80 cents a day. Per day. Okay, so that's what you're paying. Let's just say we ran it. Let's just say we're running this for 200 days a year. 0.8 times 200 equals. There's 160. So for 200 days a year, days per year. Yields $160 a year to run this guy. 2,000 watts. That's probably enough for like a room. You know, much bigger system is probably gonna run a little higher. And again, do keep in mind that most houses in North America run at an average of about 1 kilowatt.
What's 140% of 80 cents?
140% of 80 cents? Let's see, 0.8 times 1 point $1.12.
That's how much you're producing if you're paying 10 cents an hour per kilowatt. If you're gonna pay for 10 cents.
So what?
Well, if you're paying 10 cents for kilowatt hours,
Yeah.
that's how much a day that your thermal system's gonna put out. It's gonna be worth $1.12 a day.
Why?
Well, because it's 4.4, so you got 100. It's 140% of 4 hours, and then the 4.4 hours.
Oh, are you looking forward to? Are you just looking at this portion up here?
Yeah.
Oh.
It's gonna be, the difference is that's
Oh.
$1.12 a day, and this is 80 cents a day.
Yeah,
So
I think.
you're seeing how much more this system is worth as opposed to that system at 10 cents. See? So,
Yeah.
kind of hard for me to explain.
Yeah.
That.
No, I get what you're saying. I get what you're saying.
So that's what, basically, the one system's, the electric heater system's worth 80 cents a day,
Yeah.
and the other one's worth $1.12 a day.
Yeah. I think what I might have. I might have left something off of this thing. Anyway, we'll get here. There's one.
I think you put that up there after the last time I looked at it.
Well, I posted this just a week ago. I posted it on Thursday night.
Yes, yeah, it was,
one week
I
ago.
looked at everything Wednesday.
Yeah.
Sorry about that.
No, it's okay. And I think I might have to tweak it a little bit. It doesn't look like the exam has been taken yet. So, all right, so here's and I also want to change that so it looks like a superscript. Okay, so 4.4 hours of sun per day. And again, there's some pretty big assumptions here. I mean, it assumes that you're actually getting sunlight when you need it. So I said, no need for storage. We're just going to go with our 1,000 watts per square meter, and the area of the technology is 2 square meters. So there's some very big assumptions built into this, but for the sake of just comparison, let's go ahead and do this. So we've got a solar thermal tech. It is 2 square meters, and we've got 1,000 watts per meter squared. So the power of the system equals the power density, which I'll use as phi, times the area, equals 2,000 watts. So as it turns out, this technology that we are developing has the same power rating as the electric system. And again, to get energy, just equals power times time. In this case, we're getting 4.4, so equals 2,000 watts times 4.4 hours. So in this case, we're looking at 8. 0, 0, 0. No, 8,800. Yeah, why don't I get an extra 0 there? And then 1 second. Yeah, okay, so the technology is running at 1,800 watt hours per day, and that's the same as 8.8, yeah, 8.8 kilowatt hours per day. Now, so basically, this is the same as 88 cents worth of energy per day. So what's missing from the problem, though, I just realized what's missing from the problem is the upfront cost of this technology. So let's put that in, and then that'll allow us to do the simple payback. Okay, so what I just did, and I'll go ahead and repost this. I'll go ahead and repost this question, but let's look at it in Excel now. Because what I now have is the cost of the technology. You need that upfront capital cost in order to calculate it. So here's the solar portion up top. This is the existing electrical. Here's solar again, existing electrical. This is the cost of electricity, 10 cents per kilowatt hour. So this guy, all I'm doing is looking at your current cost. Your current cost per day is the 8 kilowatt hours. Where do the 8 kilowatt hours come from? Well, it's the size of the heater, 2,000, times the runtime per day that I divided by 1,000 to get kilowatt hours per day. So there's 8. Here's your cost, and then your current cost per day is 80 cents. Now, with the solar, 4.4 hours per day, there's the area, 2 meters, there's the flux, 1,000 watts per square meter. Multiply the 3 together like we just did. That's our kilowatt hours per day of solar thermal. So we're making 88 cents worth of heat per day. So what we've done, we've first of all, we've sized the system appropriately. Now, in a more complex system, you would almost certainly have it, have the system even larger, maybe double the size of your existing, double capacity. And you'd have some kind of solar thermal storage built in so that if it's not sunny, you can sort of get through the next few days. So that's how much thermal energy you're making in the equivalent of electrical kilowatt hours. So if we say we spend $200 on the technology, that means the simple days to payback is just simply the overall cost divided by what you save per day, and that gives you the days. So 227 days, and if all of our other assumptions were correct, and I started off with this problem, I said we're going to run it for 200 days per year, so the system would pay for itself in about a year. And that's really all I wanted to get out of the problem. So I'm going to go back and make that quick edit. It's ready to rock. So go ahead and solve that guy, and get the credit, and we'll move on from there.